Polar bears and polar cubs. Let's talk about the KMT, that is kinetic molecular theory. So, this theory is based on the fact that particles of matter are always in motion. So, what it tells us is that gases are very tiny particles that are far apart. All collisions between gases are elastic, meaning that there's no net loss of kinetic energy. Kinetic energy is the energy of motion, so all gas particles are always in continuous random motion. It also tells us that there's no force of attraction between gas particles. It tells us that the temperature of the gas depends on average kinetic energy, which if you think as you move, you get a little bit hot, so your temperature increases. And then how does mass affect velocity? Well, if the temperature is the same, aka kinetic energy is the same, as mass goes up, velocity goes down. So they are indirectly and exponentially related. In order to show relationships, they have to be on opposite sides of the equal sign. And finally, when it comes to if it's the same gas at different temperatures, how would the speed of the gas change? Temperature and velocity are directly and exponentially related, meaning if you have a low temp, you're going to have an even slower velocity. If you have a high temp, you'll have an even higher velocity. The two types of gases that this allows us to compare are real and ideal. Ideal are imaginary, that they're so small there is no interaction, whereas in real life there is some interaction between gas molecules. You're going to come to love this equation. You'll hear me kind of abbreviate it down to PIV, PV is the PV, and then you have the NERT, NRT, so PIVNERT. In order to make real gases act ideally, you have high temperatures. At high temperatures, the molecules are moving so fast they don't have time to interact with each other. And then at low pressures, you kind of expand the volume, which means that they have more space and they won't be able to interact with each other. Reasons why they don't behave ideally is, well, there is at low temperatures and slower velocities, there's some interaction between gas particles. And then you also then have an interaction occurring at high temperature due to the fact that you have them packed together so tightly. Here's a good example of high pressure and then low temp. Here are the three types of collisions. Inelastic collisions we don't deal with when it comes to gases, but I thought you guys might want to know that, especially if you're going into physics or are already in physics. Inelastic, either they collide, they separate, and they go in one direction, shown right here, or if it's perfectly inelastic, they combine and go in one direction. When it comes to properties of gases, you have gases. They take the shape of their container and the volume of their container. They have low densities. They're highly compressible. That's why we can put them into our car tires, footballs, basketballs. They mix rather easily, and they can diffuse or effuse, and we'll talk about the difference between those here shortly. You have gases that move like fluids. What I mean by that is they kind of just whiz by each other and don't interact. So diffusion is just random movement from high concentration to low concentration. Effusion is the same process, however, it has a tiny hole or a tiny opening in it. So, for example, you've all probably had a balloon at some point, and you leave it overnight, you leave it for a couple of days, and it starts to kind of deflate, or it starts to kind of rest closer to the ground. This is because the air within it has bounced around so much that it actually finds holes within the rubber or latex and comes through it, therefore deflating your balloon. So for number one, it's going to be diffusion because there is no tiny hole for it to move through. Because of smaller mass, if mass is smaller and kinetic energy would remain the same, that means velocity would be higher. Therefore, if a molecule is moving faster, it's more likely to be able to diffuse quicker with its higher velocity. On number two, it's going to be effuse because we're talking about a balloon. And this one, since we're at a higher temperature, Ke would then be higher. Therefore, masses are the same. So velocity would also have to increase in that one. And then finally, when talking about these conceptual problems, again, it's going to be O2 due to the fact that it has a lower mass, therefore creating a higher velocity. And then when it comes to the balloon, it's going to be the 50 degrees Celsius because higher temperature equals higher kinetic energy, meaning a higher velocity. Characteristics of liquids. They're going to be higher density than gases. They are slightly compressible, but not entirely like gases. They do diffuse, so again, higher temp equals a higher velocity so that they can move further apart. Surface tension is the existence of interaction between particles. And then we have these, so kind of liquid to gas, and then we threw in the liquid to solid, and then the gas to solid, and solid to gas. The big one that I want you to remember from earlier is evaporation and vaporization. Vaporization is liquid to gas without any heat, and evaporation, there's some applied heat. Volatile liquids, those are going to vaporize quickly. So gasoline, rubbing alcohol are some prime examples of those. Another one would be acetone for those of you that have ever been around someone when they're removing nail polish. This is just a nice, good reminder of the phase changes, and it's a phase change diagram in a way. Characteristics of a solid: you have a definite shape, definite volume. It has a specific melting point. It's highly dense, and it's incompressible. Why do I say incompressible? A solid, when you compress it, will start to break. The two types of solids that we will talk is amorphous and crystalline. Amorphous has no regular pattern, so this is glass and plastic. And then crystalline are gems and crystals. They have a known 3D pattern, and it is predictable. Finally, the last thing I want to show you is this phase change. So with this phase change diagram, this is of water. On the left is pressure, on the bottom is temperature, and it actually shows you the line at which you can actually see when a solid is melting to become a liquid, or when a liquid is freezing to become a solid. The interesting points, though, that are on here would be this triple point here, which at that moment, at that temperature and pressure, you can actually have water in all three phases coexisting within a container. And then this critical point that if you go ahead and read this, it says a point at which the highest temperature a substance cannot exist as a liquid, and then at the lowest pressure a substance can exist as a liquid. So it has to do with the fact that you're getting to a point where you're kind of blurring the lines between a liquid and a gas. All right, that's been it for the KMT. Go ahead and fill out your notes. Make sure that you have those. Your worksheet kind of goes along